C# and AI Masterclass by Edgar Milvis Volume 9, Chapter 12. Moving on to Chapter 12, Running BERT for Text Classification. Turning our attention to theoretical foundations. The theoretical foundation of running BERT for text classification locally in C# rests on the convergence of three distinct domains: the mathematical architecture of transformer models, the standardized representation of data via ONNX, Open Neural Network Exchange, and the high-performance execution environment provided by the .NET Runtime and the ONNX Runtime (ORT). To understand how we classify text using DistilBERT in C#, we must first deconstruct the journey of a raw string, like a user review, through a series of transformations until it becomes a prediction vector. Now, let's talk about the transformer architecture, attention as context. At its core, DistilBERT is a distilled version of BERT, bidirectional encoder representations from transformers. Unlike traditional recurrent neural networks, RNNs, that process text sequentially, word by word, left to right, the transformer architecture processes the entire sequence simultaneously. This parallelism is made possible by the self-attention mechanism. Imagine you are reading the sentence, "The bank of the river was flooded." If you were an RNN, you would read the, then bank, and hold that in memory. By the time you reach river, you might still be associating bank with a financial institution, creating confusion. You would have to wait until the end of the sentence to correct your understanding. A transformer, however, looks at every word at once. The attention mechanism calculates a relevance score between every pair of words in the sentence. When the model looks at the word bank, it simultaneously attends strongly to river and flooded, while paying less attention to the. This creates a dynamic context vector where the meaning of bank is weighted heavily by its neighbors. In the context of C# and ONNX, we are not training this mechanism, we are utilizing a pre-calibrated set of weights. These weights represent the statistical understanding of language learned from billions of sentences. The attention is not a piece of code we write, but a series of matrix multiplications, dot products executed by the ONNX runtime. Turning our attention to tokenization, the bridge between human and machine. Before a sentence enters the neural network, it must be translated into numbers. This process is called tokenization. DistilBERT uses a specific vocabulary, usually 30,000 plus tokens, consisting of subwords. Analogy: think of tokenization as a librarian cataloging books. Instead of cataloging by full titles, which would require a unique catalog for every possible book title, the librarian breaks titles down into common words and subwords. Unbelievable might become plus hashtag believe plus hashtag able. This allows the model to handle unknown words by breaking them into known components. In our C# pipeline, the tokenizer is the gatekeeper. It performs three critical operations: 1. Mapping, converting strings to integer IDs based on a vocabulary file. 2. Special tokens, adding CLS, classification, at the start and SEP, separator, at the end. The CLS token's final hidden state is specifically designed to aggregate the entire sequence as meaning for classification tasks. 3. Padding and truncation, neural networks require fixed-size inputs. If we batch sentences, they must all be the same length. We pad shorter sentences with zeros and truncate longer ones. Let's discuss the ONNX standard, the universal format. This is where the concept from Book 8, interoperability, becomes critical. BERT models are typically trained in Python frameworks like PyTorch or TensorFlow. To run them efficiently in a C# application, we cannot simply import the raw Python code. We convert the trained model into the ONNX format, Open Neural Network Exchange. ONNX is the PDF of AI models, a universal file format that describes the computational graph. The computational graph, an ONNX model, is a directed acyclic graph, DAG. It defines inputs, the tensors, multidimensional arrays, entering the model, e.g., input_IDs, attention_mask, token_type_IDs. Nodes, the mathematical operations, add, matmul, softmax, layer norm. Outputs, the resulting tensors, e.g., the logits for positive and negative. By using ONNX, we decouple the training environment, Python/Linux, from the inference environment, C# Windows Edge device. This is the essence of Edge AI, taking a massive, cloud-trained model and shrinking it into a portable file that runs locally on a user's machine without internet connectivity. Now, let's talk about the C# execution environment, ONNX Runtime. In C#, we utilize the Microsoft.ml.ONNX Runtime NuGet package. This package provides the inference session class, which is the engine that executes the ONNX graph. Why C# and .NET for this? 1. Span T and memory management. When processing text, we deal with arrays of integers, token IDs. Modern C# allows us to use span T and memory T to manipulate these arrays without unnecessary heap allocations. This is vital for low-latency inference on edge devices where garbage collection, GC, pressure can cause frame drops or UI freezes. 2. Disposable pattern. The ONNX Runtime manages unmanaged resources, GPU memory, C++ execution providers. C# using statements ensure that the model session and tensor memory are released immediately after inference, preventing memory leaks in long-running applications. 3. Async/await. While inference itself is synchronous, blocking, for a single prediction, the pre-processing, tokenization, and post-processing, interpreting logits, can be offloaded. However, for real-time edge inference, we often use synchronous execution to minimize thread context switching overhead. Moving on to theoretical foundations. Let us visualize the flow of data through the system. This diagram illustrates a synchronous inference pipeline where data flows sequentially through stages, pre-processing, model execution, and post-processing, to minimize thread context switching overhead for efficient real-time edge processing. Now, let's explore 1. The input tensor construction. The ONNX model expects specific input names, usually input_IDs, attention_mask, and sometimes token_type_IDs. Input_IDs, the sequence of integers representing tokens. Attention_mask, a binary tensor, zeros and ones, telling the model which tokens are real data and which are padding. Without this, the model would try to derive meaning from the padding zeros, diluting the result. Analogy: imagine a lecture hall. The input_IDs are the students sitting in chairs. The attention_mask is a roll call. If a chair is empty, padding, the attention_mask tells the professor, the model, to ignore that chair entirely when taking attendance. Let's discuss 2. The execution providers. When we create an inference session in C#, we can specify an execution provider. This is the bridge to hardware acceleration. CPU, the default. Uses the CPU's AVX instructions. Good for compatibility but slower. CUDA, NVIDIA offloads matrix multiplications to the GPU. Essential for large models or batch processing. DirectML, Windows hardware agnostic GPU acceleration for Windows devices, AMD, Intel, NVIDIA. OpenVINO, Intel optimized for Intel CPUs/NPUs. In an edge AI scenario, e.g., a C# WPF application on a laptop, we might dynamically select the provider based on available hardware. If an NVIDIA GPU is detected, we use CUDA, otherwise, we fall back to CPU. Let's discuss 3. The inference step. Once the ORD value, a wrapper around the tensor data, is created from our C# arrays, we call session, run. The ONNX runtime, written in C++ for speed, takes over. It traverses the graph. It performs the matrix multiplications defined by the model weights. It applies activation functions, GELU, TAN. It calculates the softmax function at the final layer to convert raw scores, logits, into probabilities, 0 to 1. Now, let's explore 4. Post-processing. The model returns a tensor of shape, 1, 2, batch size 1, classes 2. We extract these values in C#. Index 0, logit for negative index 1, logit for positive. We apply the softmax function if it wasn't baked into the model output, $$text, softmax, x_, equals \frac, x_, sum_, j, x_j, $. This gives us a confidence score. We then map this back to a human-readable label. Now, let's talk about why this matters for edge AI. The theoretical importance of this pipeline in the context of edge AI is latency and privacy. 1. Latency. In a cloud-based scenario, sending text to an API, waiting for the server to process it, and receiving the response introduces network latency, often 100 milliseconds to 500 milliseconds. Local inference via ONNX runtime on a CPU can complete BERT inference in less than 50 milliseconds. 2. Privacy. Since the text never leaves the user's device, sensitive data, medical notes, private messages, remain secure. 3. Offline capability. The application functions without an internet connection, crucial for industrial IoT or remote field work. Now, let's explore summary of concepts. To summarize the theoretical foundation, 1. DistilBERT uses the transformer architecture and self-attention to understand context bidirectionally. 2. Tokenization converts natural language into a fixed-size numerical representation, handling sub, words and padding. 3. ONNX serves as the universal container, abstracting the model architecture from the training framework. 4. ONNX Runtime in C# provides the engine to execute these graphs, leveraging hardware acceleration, CPU/GPU, via execution providers. 5. C# features like span, T, and I disposable ensure that memory management is efficient and safe, which is paramount for maintaining high frame rates in UI applications or handling high throughput in services. This theoretical framework sets the stage for the practical implementation, where we will translate these concepts into code, loading the model and processing real-world text data. Now, let's explore basic code example. We begin by importing necessary namespaces. Notice at lines 1 and 2, we bring in Microsoft.ml.ONNX Runtime and Microsoft.ml.ONNX Runtime, tensors. These are crucial because they provide the core functionalities for interacting with ONNX, Open Neural Network Exchange, models, specifically for loading, running, and managing tensor data within the ONNX runtime. Without these, we wouldn't be able to perform local inference with our pre-trained BERT model. The other using statements are standard C# libraries for general utility, collections, and text manipulation, which are common in many applications. Here, we define our BERT sentiment analysis namespace and the program class, which contains the entry point of our application, the main method. The comments at lines 11 to 13 clearly state the purpose, to demonstrate a self-contained BERT-based sentiment analysis pipeline. This structure is typical for console applications in C#, where main is the first method executed. Inside main, we will orchestrate all the steps from text input to sentiment prediction. At lines 18 to 25, we define our input text and the path to our ONNX model. The input text at line 18 is the piece of text we want to classify. This is our raw data, the starting point of the pipeline. Crucially, at line 24, we specify model path. This highlights a key architectural decision: we are using a pre-trained ONNX model. This means the heavy lifting of model training has already been done, and we are leveraging a highly optimized, portable format for inference. The note at lines 21 to 23 is vital. It reminds us that the ONNX model file must be present in the execution directory. In a production environment, this model might be deployed alongside the application or fetched from a model repository. Using ONNX allows for cross-platform and cross-language deployment, making our solution flexible. Lines 27 to 34 introduce the tokenizer. At line 29, we instantiate basic BERT tokenizer. This is a critical component in any NLP pipeline using transformer models like BERT. The encode method at line 33 takes our raw text and transforms it into numerical representations, token IDs, attention masks, and token type IDs, that the BERT model can understand. The comment at lines 27 to 28 is very important. It explicitly states that this is a simplified tokenizer for demonstration. In a real-world scenario, we would use a robust, pre-built tokenizer library, e.g., from Hugging Face's tokenizers library or Microsoft.ml tokenizers. Why? Because real tokenization, especially wordpiece or BPE, is complex, handling subword units, special tokens, and vocabulary lookups efficiently. Our basic BERT tokenizer serves to keep the example self-contained but would not be suitable for production due to its simplicity and limited vocabulary. At lines 36 to 42, we create an inference session using Microsoft.ml.ONNX Runtime. This is the core component that loads the ONNX model and prepares it for execution. Notice the using statement at line 37, using var session equals new inference session, model path. This is a C# best practice for managing unmanaged resources. Inference session objects often wrap native code and memory allocations, so ensuring they are properly disposed of, even if an exception occurs, prevents memory leaks and resource exhaustion. Without using, we would need to manually call session, dispose, which is error-prone. This decision is crucial for application stability and efficient resource management, especially in long-running services or applications with frequent model inferences. Lines 44 to 50 are where we prepare the inputs for our BERT model. We create a list named onxValue, which is the expected input format for inference session, run. BERT models, by design, typically require three specific inputs: input_IDs, attention_mask, and token_type_IDs. These are directly created from the encoded input generated by our tokenizer. Input_IDs are the numerical representations of our tokens. Attention_mask tells the model which parts of the input are actual tokens and which are padding, allowing the model to ignore padding during attention calculations. Token_type_IDs are used to distinguish between two sentences in tasks like question answering, but for single sentence classification, they are typically all zeros. Providing these correctly is fundamental for BERT to interpret the input sequence as intended. A mismatch here would lead to incorrect or nonsensical predictions. At lines 52 to 57, we execute the model inference. Session, run, inputs, is the call that passes our prepared input tensors to the ONNX runtime, which then performs the forward pass through the neural network. The result, results, is an idisposable object, hence the using statement again at line 53. This reiterates the importance of resource management when dealing with ONNX runtime outputs, which might also hold unmanaged memory. The results object contains the raw outputs, logits, from the final layer of our BERT model. This is where the magic happens. The model processes the numerical inputs and produces its prediction in the form of raw scores. Lines 59 to 69 focus on processing the model's raw output and presenting the results. At line 57, results, first, .AstInsert float extracts the primary output tensor, which contains the logits. Logits are raw, unnormalized scores. To convert these into meaningful probabilities that sum to 1, we apply the softmax function at line 60. This is a standard practice in classification tasks. We then interpret these probabilities. At line 63, we assume index 0 corresponds to negative and index 1 to positive, a common convention for two-class sentiment models like those fine-tuned on SST2. If the positive probability is greater than 0.5, we classify it as positive. Finally, lines 67 to 69 print the input text, the predicted sentiment, and the confidence scores. This clear output allows us to immediately understand the model's decision and its certainty, which is crucial for evaluating its performance. The softmax helper method, defined at lines 72 to 80, is essential for transforming the raw output logits from our BERT model into a probability distribution. Logits can range from negative infinity to positive infinity, but probabilities must be between 0 and 1 and sum to 1. The softmax function achieves this. Notice the max operation at line 76 and subtracting it from each logit before exponentiation, math, exp, x, max. This is a common numerical stability trick. Without it, very large positive logits could lead to exp overflowing, returning infinity, and very large negative logits could lead to underflow, returning 0, both causing issues in the sum. By subtracting the maximum, we ensure that the largest exponent argument is 0, preventing overflow, while maintaining the relative differences between the logits, thus preserving the relative probabilities. This is a critical detail for robust numerical computation in machine learning. At lines 82 to 97, we define our basic BERT tokenizer class. The XML documentation comment at lines 84 to 86 is important as it clearly states its purpose, a simplified tokenizer for demonstration. It also explicitly advises using robust libraries in real-world applications. The private _vocab dictionary at lines 88 to 97 is a crucial part of this tokenizer. It maps common words and special BERT tokens, CLS, SEP, PAD, to their corresponding integer IDs. This vocabulary is extremely limited for demonstration purposes. In a real BERT model, the vocabulary would contain tens of thousands of entries and be loaded from a vocab.txt file. The choice to hardcode a small vocab here simplifies the example but also highlights a significant limitation. Any word not in this tiny vocabulary will be handled as an unknown word, severely limiting the tokenizer's practical utility. This design choice prioritizes clarity and self-containment over real-world performance or accuracy. The encode method, starting at line 99, is the heart of our basic BERT tokenizer. It takes raw text and a maxlen, maximum sequence length, and converts the text into the numerical tensors required by BERT. At line 101, we perform a very basic text normalization, converting to lowercase and splitting by common delimiters. This is a simplification. A real tokenizer would involve more sophisticated punctuation handling, lowercasing rules, and potentially subword tokenization, like word piece. At line 105, we add the CLS token ID. This classification token is a special BERT token placed at the beginning of the input sequence. Its corresponding output embedding is often used as the aggregate representation of the entire input for classification tasks, making it a fundamental part of how BERT processes single-sequence inputs. Lines 109 to 124 continue the tokenization process within the encode method. We iterate through the words, derived from the input text, and attempt to look up each word in our _vocab dictionary. At lines 111 to 113, if a word is found, its corresponding ID is added to token IDs. This is a direct lookup, which is simplistic. In a true word piece tokenizer, words not found would be broken down into subword units until all units are in the vocabulary. At lines 115 to 119, if a word is not found, we assign it the ID 100, which typically represents the UNK unknown token in BERT vocabularies. This is an important fallback. Without it, unknown words would cause errors. Finally, at line 123, we add the SEP token ID. This separator token marks the end of a sequence, indicating to BERT where the meaningful input ends, which is crucial for defining the boundaries of the input text. At lines 126 to 137, we move into the crucial step of padding and creating the attention mask. BERT models expect fixed-length inputs, so we initialize 3 arrays, input IDs, attention mask, token type IDs, to max len. At lines 131 to 137, we iterate through our token IDs and populate these arrays. Input IDs gets the actual token IDs. Attention mask gets 1 for each real token, indicating to the model that these positions should be attended to. Token type IDs gets 0 for all tokens, as we are performing single-sentence classification and don't need to distinguish between 2 segments. This process is vital because transformer models operate on fixed-size tensors. Padding ensures that all inputs conform to this fixed size, and the attention mask prevents the model from wasting computation and learning from the padding tokens, which are semantically meaningless. Lines 139 to 145 complete the padding process. After copying the actual token IDs, we iterate from the end of the token IDs list up to max len. In this loop, we fill the remaining positions of input IDs with the pad token ID, which is 0 in our underscore vocab. Concurrently, we set the corresponding attention mask entries to 0. This explicitly tells the BERT model, these positions are just padding, ignore them during self-attention calculations. The token type IDs also remain 0. This padding strategy is standard for BERT inputs and is essential for batching multiple sequences of varying lengths into a single tensor for efficient processing on GPUs or other accelerators. Without correct padding and masking, the model would either error out due to mismatched input dimensions or produce nonsensical results by attending to padding tokens. At lines 147 to 159, we convert our raw integer arrays into dense tensor objects, which are the specific tensor types expected by ONNX Runtime. Notice the constructor new dense tensor int, input IDs, new, 1, max len. The new, 1, max len, specifies the shape of the tensor. This, 1, sequence underscore length, shape is critical because BERT models typically expect inputs to be batched, even if it's a batch of 1, hence the 1. If we were processing multiple sentences simultaneously, the 1 would be replaced by the batch size. This reshaping is a common requirement when interfacing with deep learning models, as they are designed to process data in batches. Finally, at lines 153 to 158, we encapsulate these 3 tensors into an encoded input object, which provides a clean and structured way to return all the necessary BERT inputs from our tokenizer. Finally, at lines 162 to 168, we define the encoded input class. This simple class acts as a container or data transfer object, DTO, for the 3 essential input tensors that BERT models require, input IDs, attention mask, and token type IDs. By encapsulating these together, we create a clear and convenient way to pass the tokenized and prepared input data throughout our pipeline. This improves code readability and maintainability, as methods can simply accept or return an encoded input object rather than managing 3 separate tensor parameters. This is a good practice for organizing related data, especially when dealing with complex data structures like those used in deep learning. By scanning this code you can go to the website with more details and with buying options. On leanpub.com you can find the discounted bundle with all the volumes. This lesson is excerpted from Volume 9, Chapter 12 of the C# and AI Masterclass ebook series and from the volume Edge AI and Local Inference. Running LLMs, Llama/Phi, locally with C# and ONNX. You can find all source code here, https://github.com/edgarmilvis/C# programming series. The ebook includes 20 chapters, each one with diagrams, advanced examples, and 5 exercises with solutions. Subscribe to the channel to watch more videos. Thank you for your attention. I look forward to seeing you in the next lesson.